Hi there, welcome to this third in the short series of videos in relation to cable sizing. In this video, we're going to look at verification of voltage drop, this time in the scenario of, for example, a periodic inspection. Remember, for initial verification, generally voltage drop is confirmed by the designer through their calculations. In a periodic inspection, you might need to then verify that the circuits meet the requirements for voltage drop. So in this initial video, we're going to look at calculations of voltage drop using the circuit impedances, the R1 plus Rn values, and other ways in which we can actually measure that voltage drop. So voltage drop in a single phase circuit, when it comes to calculation, it can be calculated using the following equation. The volt drop equals the design current times the resistance, or the sum of the resistances of the line and neutral conductors. Okay. So voltage drop itself, how can we determine voltage drop? Well, we can either do it by direct measurement or by calculation. If we're looking down the direct measurement route, we need to carry out simultaneous measurements at the origin of the supply and at the load terminals of the circuit. Okay, direct measurement takes into account the voltage drop in distribution circuits and any allowable variable variations in the public supply. Remember, we've got that plus 10%, minus 6%. This simultaneous measurement, although difficult, is not impossible, but generally for most periodic inspections and testing, we would generally look at using the calculation route. Okay. So in order to calculate voltage drop, the first thing that we need to consider is how do we obtain these R1 plus Rn values in our calculation that we looked at previously? Well, we can find our R1 plus Rn values through either direct measurement or by carrying out some calculations. Direct measurement, obviously similar test to the R1 plus R2 test, where you're making sure the circuit's isolated at the board, disconnecting your line and neutral conductors, connecting them up together, and then testing at the end of the circuit between the line and neutral to obtain your R1 plus Rn values. If you've previously measured an R1 plus R2 value on a circuit where the CPCs are the same size, same cross-sectional area as the live conductors, then you can utilise that value rather than actually carrying out another test. Obviously, that we have to take into account whether or not there's going to be excessive parallel paths in the CPC. Okay. Once we've obtained those R1 plus Rn values, you then multiply that by a correction factor of 1.2. Remember, you're measuring the cables at 20 degrees C. We need to increase the temperature of those cables from 20 degrees C up to 70 degrees C for thermoplastic cables to take into account the positive temperature coefficient of 0.004 ohms per ohm per degree C. Okay, for copper. All right. So when we have or we don't have access to that test, or we don't want to do that test, another way in which we can obtain our R1 plus Rn values is to actually calculate the R1 plus Rn values, and we use it shown with that equation there. We take 2 times the milliohm per meter value for the line conductor's resistance times the length times that correction factor of 1.2 and then divide it by 1,000, obviously, because we're utilizing milliohms per meter. Okay. As I said, the milliohms per meter value, we're just utilizing the line conductor, so we can use 2 times that value for the line and the neutral. All right. So if you look here, you'll see we've got a 1.5 millimeter squared cable. In order to find the R1 plus Rn value for any given length, I would take 2 times the milliohm per meter value for the line conductor, multiply it by the length, multiply it by 1.2, and then divide it by 1,000, and that would give me the R1 plus Rn calculated value. Likewise, in order to negate the need for doing this 2 times value, if you look at the 1.5 and 1.5 there, Remember, in your tables, this second column will say protective conductor, but it's just as well being the line and the neutral if it's the same size. Then we can disregard that 2 times value because the table's already carried out that calculation for us. Okay, so we can use the two conductors together for the R1 plus Rn value. All right, and disregard the 2 times. But again, we're still multiplying it by the length of the run and that correction factor. Okay. So I've got a wee example here. I've got a shower circuit. It's 30 meters in length. And it's running 6 millimeter squared copper conductor. The load current is 39 amps, and we're looking to calculate the volt drop. Okay, so obviously, in order to get to the voltage drop, the first thing we need to find is the R1 plus Rn value. Now we have the length of the run. Yeah, we'll know the correction factor of 1.2, taking that as the general terms because we're going from roughly 20 degrees C up to 70 degrees C. So what we need to find first is the milliohm per meter value. So we find those in table B1 or in the guidance note 3 or I1 in the on-site guide. We have a 6 millimeter squared conductor. Therefore, we're going to use a milliohm per meter value for that conductor of 3.08 milliohms per meter. Okay, so we take 2 times that 3.08 times the 30 meters in length times the 1.2, the correction factor. Remember, it doesn't matter whether we do the correction factor here or here; it still works its way through, and that gives us an R1 plus Rn value, remember to divide it by 1,000 once we're finished, of 0.222, okay, ohms. Now remember, we've corrected it for temperature, okay, so that's now at 70 degrees C, so that's the cable running fully loaded, okay. So we take that cable running fully loaded and that cable resistance for the R1 plus Rn, and we drop it into our volt drop calculation. Now in the example given, we've got a 39 amp load, and we multiply that by the 0.222 ohms. Okay, that gives us an actual volt drop for this circuit of 8.66 volts. Now this circuit, the maximum volt drop that we can allow for this circuit, because it's not a lighting circuit, is 5% of the supply voltage. So we'll take that as 230 volts. So 5% of 230 volts is 11.5 volts. So you'll see there the volt drop, the 8.66 volts that we've calculated here, taking into account that temperature correction, is 8.66 volts, which is less than that 11.5% max that we're allowed. Okay, so hopefully that will help you with some volt drop calculations. Remember, there are plenty of examples in your folder. If you're running into any difficulties, you know how to get in contact.